morning, students. This is the lecture number 3. The title of this lecture is Graphical Method. Till now, we have seen how we can model real life problems into linear programming problems. We have also seen the definition of a general linear programming problem of n variables. As a special case, the two-dimensional linear programming problem can be solved with the graphical method, and that is what we are going to study today. The outline of this talk is as follows. We will first look at the definition of a two-dimensional linear programming problem. Then we will study the 4 cases that are likely to arise while solving a two-dimensional linear programming problem, and finally, we will look at some exercises. So, first of all, let us look at the definition of a two-dimensional linear programming problem. It states that we want to minimize or maximize C1 x1 plus C2 x2 subject to A11 x1 plus A12 x2 less than or equal to B1, and similarly A21 x1 plus A22 x2 less than or equal to B2, and like this we could have m number of constraints, that is am1 x1 plus am2 x2 less than or equal to b2. x1 and x2 are the decision variables and they have to be greater than or equal to 0, and all the aij's and the b's and the c's, they have to be real numbers. So, while solving, we will see that there are 4 possibilities. The first one is the unique solution, second one is the multiple solutions, third unbounded solution, and finally infeasible solution. So, let us look at each of these cases separately. The first example that we will study is for the unique solution case. Now, the problem is as follows. We have to maximize 5x1 plus 3x2 subject to x1 plus x2 less than equal to 5, 3x1 plus 8x2 less than or equal to 24, and x1 and x2 greater than or equal to 0. Now, this indicates that we are interested only in the first quadrant. So, we will first plot the x axis on the horizontal axis, that is the x1 variable will be represented on the x axis and the vertical axis will represent the x2 variable. The origin will be denoted by 0 0 O. Now, first let us look at how we will plot the first constraint, that is x1 plus x2 less than or equal to 5. This can be plotted as follows. This is the straight line passing through the 2 points 0, 5 and 5, 0. Now, as you probably know that a line uniquely passes through 2 points, and this can be obtained by putting x1 equal to 0 and getting the corresponding value of x2. Similarly, putting x2 equal to 0 and getting the corresponding value of x1. So, this line that we have plotted joining 0, 5 and 5 0 is the straight line x1 plus x2 is equal to 5, but we are interested in knowing which side of this straight line is the feasible region, whether it is below the line or whether it is above the line. This can be determined by substituting the origin into the inequality x1 plus x2 less than or equal to 5, and when you substitute the origin 0, 0 onto the inequality x1 plus x2 less than or equal to 5, you get 0 is less than or equal to 5. Now, then you have to evaluate whether this is true or not. If this is true, that means the origin belongs to the feasible domain, and in this case the origin belongs to the feasible domain. Therefore, the feasible domain is below this line. This is indicated by this arrow, and it says that the feasible domain is below the line. Like this, we will plot the other constraints as well. So, what is the next constraint? This is again the straight line which represents the second constraint, and it passes through the 2 points 0, 3 and 8, 0. So, again we will make a decision whether the feasible domain lies below the line or above the line. This can be determined by substituting the value of the origin in the inequality, and it tells us that again the feasible domain is below the line. Now, since there were only 2 constraints in the given problem, therefore, the feasible domain has to be the intersection of the region that is covered by both these constraints, and this is determined by the 2 lines like this, the 4 points A, B, C and O. Now, you can easily determine the coordinates of the point B by solving the equations represented by the constraint, and the coordinates of B are as follows, that is 16 by 5 and 9 by 5. So, the feasible region is nothing but the points given by A 0, 3, B 16 by 5 and 9 by 5, C 5, 0 and O the origin, that is 0, 0. Usually it is a good practice to shade this region. Now, this is the feasible domain, and all points belonging to this region will satisfy the constraints of the problem. But the question is, which point will give us the optimum value? By optimum value, I mean the maximum value of the objective function. Now, for this we will evaluate the value of the objective function at each of these points, the corner points A, B, C and O, and try to get what is the value of the objective function at each of these points. Also, we will try to draw the family of straight lines which represent the objective function. So, this is the family of straight lines which represents the objective function. They are all parallel because we know the slope and we do not know the right hand side. So, by varying the right hand side of the objective function, we can easily draw the family of straight lines which represent the objective function. Now, the solution to the problem is that member of this family of straight lines which is intersecting the feasible domain and which is farthest from the origin, because this is a maximization problem. Had it been a minimization problem, we would have chosen that member of the of this family of straight lines which is nearest to the origin. But in this case, since our objective function is maximization, so we will be interested in that member of this family of straight lines which is farthest from the origin and at the same time which intersects the feasible domain. And which is that member? This is the member that is highlighted, this one, and it is intersecting the feasible domain at this point C, that is C 5, 0. So, this is the solution of the problem. Now, in this table I have tried to locate the corner points of the feasible region, that is O 0, 0, A 0, 3, B 16 by 5 and 9 by 5 and C 5, 0. And on these points I have tried to evaluate the value of the objective function, that is 5 x 1 plus 3 x 2, and you can see that at the point origin the value is 0, at the point A the value of the objective function is 9, at the point B the value of the objective function is 21.4 and the value of the objective function at the point C is 25. Now, we will look at each of these values and we find that the maximum occurs over here, that is 25 is the largest. So, 25 is the maximum, and this indicates that the solution is obtained at the point C given by 5, 0. So, therefore, this indicates that the solution to the problem is x 1 is equal to 5, x 2 is equal to 0 and the objective function value is 25. Now, in the second example that I will be talking about, we have the case of a multiple solution. Exactly in the same way, the objective function is changed here, maximization 3 x 1 plus 8 x 2, x 1 plus x 2 less than or equal to 5, 3 x 1 plus 8 x 2 is less than or equal to 24, x 1 and x 2 are both greater than or equal to 0. Now, you will observe that the slope of this second constraint, that is 3 x 1 plus 8 x 2, is the same as the slope of the objective function. So, this indicates, in fact, before solving the problem you can conclude that since the slope of the objective function is the same as the slope of one of the constraints, therefore, this problem is likely to have multiple solutions. So, as before, let us look at how we can plot this problem on the two dimensional space. So, as before, this is the x 1 axis, this is the origin, this is the x 2 axis. We will plot each of the constraints, and this is the first line, and again these are the points 0, 5 and 5, 0, and again as before the region is below the line. The second constraint is given by this line segment. It passes through the 2 points 0, 3 and 8, 0. The point of intersection of these two lines is B 16, 5 and 9, 5, and the feasible domain is the intersection of both these constraints, that is the region which is common to both these constraints. So, the feasible region is given by A 0, 3, B 16 by 5, 9 by 5, C 5, 0 and O 0, 0, and the feasible region is the same as before. I have particularly chosen the same problem to indicate how the same problem may have different objective functions, and accordingly the solution will also be different. So, we will look at the family of straight lines which represents the objective function for this problem, and we find that these are the straight lines which represent the objective function, and as you can see they are parallel to the second constraint. Out of this family of straight lines, the one that is intersecting the feasible region, that is going to give us the optimum solution, and you can see that the solution, the optimum solution will lie on these 2 points A and B. So, the solution lies on the points A and the point B, and in fact it will lie, the solution will lie on all points on the line segment joining A and B. Let me repeat, it will the solution will lie not only on A and B, but also it will lie on all points lying on the line segment A and B. And in fact, how many such points are there on the line segment A and B? Can you count these points? Yes, you cannot count these points, and in fact there are multiple number of points which lie on the line segment A and B, and all of them will give the maximum solution. That is why this kind of cases is sometimes called as multiple solution cases. Now, looking at the vertices of the feasible region and their corresponding objective function value, we find that at the origin the value is 0, at the 2 points A and B the value is 24, the value of the objective function is 24, and at the point C the value of the objective function is 15. Now, this indicates clearly that the highest value amongst all these 4 is being attained at these 2 points. So, 24 value is being attained at both these points A and B, and as I said before, if you take any other point on the line segment A and B, you will find that that point will also give a value 24. So, I can leave this as an exercise for the students. Choose any point on the line segment A and B. How will you choose a point? You know the equation of the line AB. So, you can choose a point, any point on the line segment AB, and substitute in this objective function, you will get 24 as its objective function value. Now, the third example that we are going to study is the case of the unbounded solution. You will find that in this problem we have maximization of 3x1 plus 8x2 subject to 2x1 minus x2 less than or equal to 0, and we have x2 less than or equal to 4 and x1 and x2 are both greater than or equal to 0. So, let us plot these two constraints on the x1 x2 axis. So, as before, this is the x1 axis for the first variable, this is the x2 axis for the second variable, and this is the line which represents the first constraint, and as before we will look at what side of the region what side of the line is the region. Now, since it is passing through the origin, as I mentioned earlier, we will substitute the origin to determine which side of the line is the feasible domain. But in this case this line is passing through the origin. So, we cannot substitute the origin to find out which side of the line is the feasible region. Therefore, in such cases we will choose any other point other than the origin. For example, you choose let us say 5, 0, 5, 0 is a point which we know is on the x axis. So, we will substitute 5, 0 into this equation of this line, and we find that it satisfies this line. Therefore, the feasible region is below the line. Next, we will plot the second line. These are the points. O is the 0, 0 is the origin, A 2, 4 is the intersection of the first constraint and the second constraints. So, this is the second constraint, x 2 is equal to 4, and as before it is below the line, the feasible region is below the line. And if you look at the coordinates of these points that lie on the uppermost line, that is it is B, I have written t, 4. Now, t, 4 represents that for any value of t greater than or equal to 2, we can represent a point B by the coordinates t, 4. Similarly, the point C is on the x1 axis and it can be represented by the point t, 0. So, what you find that the feasible region is given by A 2, 4, B t, 4, C t, 0 and O 0, 0. So, as before, let us shade the feasible region, and that is the feasible region. Now, the feature about this feasible region is that it is unbounded. How is it unbounded? It is extending towards infinity on the right hand side. So, this indicates that the reason is the feasible region is unbounded on the right hand side. Now, coming to the family of straight lines which represent the objective function, let us plot this family. This is the first member of this family of straight lines which represents the objective function. This is the second member, the third member, and so on. But what do you observe? You observe that no matter which member of this family of straight line you choose, the value of the objective function will keep on increasing and increasing and increasing up to infinity, and that means that the problem has a unbounded solution, because our objective function is maximization. Please note, had it been a minimization problem, then probably the solution would have lied on the lower side, that is on the origin in this particular case. But since it is maximization, therefore, the value of the objective function will keep on increasing and increasing. This can be represented in the form of this table which I have shown here. As before, the value of the objective function at the point O 0, 0 is given by 0. the value of the objective function at the point 2 comma 4 is given to be is obtained as 38. Similarly, the value of any point B given by t comma 4 is like this 6 plus 8 t. So, if you substitute this in that equation, you will get 6 plus 8 t. Similarly, the value of the objective function at the point C given by t comma 0 is 8 t. Now, you find that if you substitute any value of t greater than 2, you will keep on getting higher and higher values of these expressions, and obviously this one is higher than this one. So, therefore, we can conclude that this point B is it can be increased and increased as and how the value of t is increased, and that is the reason why that as t increases, it 6 plus 8 t also increases, and this means that the problem has a unbounded solution. The fourth example that I am considering is the case of an infeasible solution. Now, what is the characteristics of this problem? Maximization of 3x1 minus 2x2 subject to x1 plus x2 less than equal to 5, x1 plus x2 greater than or equal to 6, and x1 and x2 are greater than or equal to 0. So, as before, let us try to draw the feasible domain. This is the x1 axis, this is the x2 axis, and this is the origin. The first constraint is represented by this straight line, and the region is below this line. This line is passing through the points 0, 5 and 5, 0, and the feasible region is likely to lie below the line. Again, the second constraint is represented by this straight line, and this straight line passes through the 2 points 0, 6 and 6, 0, and the feasible domain is expected to lie above this line. And as you can very well see that the feasible domain lies below the first line and it lies above the second line, and we find that there is no common region or no intersection of these two lines. Therefore, the feasible domain of this problem does not exist, and we say that the solution of the problem is infeasible, no matter what the value of the objective function is. Therefore, we say that this is the case of a infeasible solution. So, based on the 4 cases that we have studied, I would like you to solve these 3 examples at your homes. We need to solve the following LPP using the graphical method. The first problem is maximization of 5x plus 8y subject to 3x plus 2y greater than or equal to 38, 3x plus 4y greater than or equal to 24, x and y should be greater than or equal to 0. I have given the answers for the problems for you to check. The first problem has the answer 0, 18. Similarly, the second problem is minimization of 5x plus 2y. This is subject to x plus 4y greater than or equal to 4, 5x plus 2y greater than or equal to 10, and both x and y should be greater than or equal to 0. As you can see, that the slope of the objective function is the same as the slope of the second constraint, and hence it indicates that this is a case of a multiple solution. So, the multiple solution exists on the points lying between 0, 5 and 16, 9 and 5, 9. And the third problem is maximization of 5x minus y subject to 2x plus 3y greater than or equal to 12, x minus 3y greater than or equal to 0, x and y are greater than or equal to 0, and you will find that the answer to this third problem is unbounded. So, I request you all to please use graph paper and a pencil and a rubber to solve these problems on the graph paper, and make a habit of shading the feasible region and also determining the vertices of the feasible region, and then plot the values of the vertices in the form of a table and obtain the corresponding value of the objective function. This way you will get the final solution. So, that completes this lecture. Thank you.